Hi, everyone. Welcome to today's masterclass on working with time and frequency with Matlab. Thanks for joining me today. My name is Loren, and I've been at MathWorks for over 30 years. I try to share my knowledge in classes like today's, and in addition, I have a website, a blog on our MathWorks website called The Art of Matlab, where you may find many more useful tips and tricks and insight into Matlab. So let's get started on this week's topic. This is meant to be fairly introductory, but hopefully there will be some stuff that's useful to people who maybe already are using Matlab for some signal processing. So my agenda today is to talk about what happens when you need to do data analysis with Matlab. And by the way, your data happens to be a signal and not just a plain old set of numbers or just measurements from the lab in one at a time sort of thing. And the demo I'd like to do today is a dual tone phone decoding application, which many of you, if you've studied some audio or some EE, you might have seen this in a class already. And it'll give us a chance to do a little introduction to the Matlab environment and build a way to understand what's going on with the phone numbers that we hear when they're pressed, and how to create documentation and create graphical applications from these. So I'm going to start off with what is sort of generic, which is that the first thing we need to be able to do is get access to the data. Actually, without your data, doing any sort of work would be less meaningful. So that could be whether or not we use files, whether you have data in a database, whether or not you're getting it from a live feed from hardware or Internet of Things. And after you get that, you bring it into Matlab and you spend a bunch of time exploring and discovering. And that's where we're going to spend a lot of time today, trying to figure out how to extract which key got pressed based on the tones that we hear. So we'll spend a bunch of time there. And then we're all done. We probably have to tell someone in some way what we've done, whether it's through creating a report, which I'll do, creating some outputs. Maybe we just need some filter coefficients to hand to someone, or maybe we want to deploy it in some sort of way. But you probably know that for most of us, we don't find the right algorithm or one we're happy with instantly. And so what we need to do is figure out how to automate that cycle, because parts of it we may be set with. And if then someone gives me a directory with thousands of audio signals, I don't want to have to do and go through hand by hand and analyze each one of those separately. So I'd like to find a way to automate it. So let me go into a little more detail about what the demo will be. First of all, I'm going to come to Matlab very briefly here. This is the document that basically we're going to try to create. You can see I'm talking about dual tone decoding. I've got a picture of a phone here, and you'll see we get some signal, and then we're looking at things in the frequency domain, and we're trying to understand what the different tones are. So when they're all done, we end up with a phone number. So that's our goal, is to be able to create some sort of document in the end that will tell us, given this data, what kind of output would we get? And so the idea is, again, to determine the phone number from the touch tone audio signal. So we're going to need to do a bunch of signal processing in order to make this work. We're going to need to filter and process the signal. We might need to do something. Part of the reason we might need to filter is not all the time is our data perfect, in fact, rarely. And so we need to do something. Maybe there's a noise source and we want to get rid of it. And then we need to come up with our decoding algorithm, and then document the analysis in a file and figure out how to apply that to many, many files after a while. So let me tell you a little bit more about dual tone phone number detection. You can see here a keypad that's like on a phone. And if I zoom in, you'll see I put the frequencies, and each column has its own frequency and each row has its own frequency. So when I push a particular number, I get two frequencies, one for the rows and one for the columns. And so that's what our goal is, to try to detect those two frequencies so we can figure out which button got pressed. And again, our approach is going to be to use some signal processing techniques like spectral analysis, digital filtering, finding peaks, and thresholding to make that happen. So I'm going to come over here to Matlab now. And I'm not going to even start with that document that we have there. That would be a little bit unfair. But I want to show you in my current folder, I actually have some data. I have a source signal CSV. Whoops. Come back. Let me open that. And when I open it, you'll see it opens the import tool. And it gives me a bunch of information. And if I want to, I can just say import selection. And well, now I have here a table with the information. We look in the table and you can see it's got the data associated with it and then all of these numbers. Well, the nice thing about the import tool, where did it go? Here, come over to my Matlab. Here is that there's what happened when I double clicked on it is Matlab tried to figure out the best it could how to read in this information. But really, I don't need the date for that name. I'm going to just make my signal X. And you'll notice that we are by default putting it in a table. Now, a table is an interesting thing. It's an M by N array, kind of like a matrix, only each column can be different kinds of data. In this case, we only have one column, so we don't need the complexity of that. And I can import my selection now. And when I do, when we come over here, you'll see I've got X and I've got the source signal. And it's the same data, just represented in two different ways. Okay, so let me come back here one more time. If I think about wanting to read in this data automatically, it's going to be a pain if I have to click on it every time. And here's a compelling reason why I may need to. You'll see I have a folder here with data, and I've got a whole bunch of other files there that we may want to read. And of course, it could be many, many more than this. And so we'd like to find a way to automate that. And as is very typical in MATLAB, from our tools, there's usually an option to not just do the task that you're doing, but to also automate it by creating either a live script, a script, or a function. So let me generate a script first. And this code just got generated. It is, in fact, a little bit after 11 a.m. where I am right now. And it tells me, if we look through here, you can see all the different options that were in there. There wasn't a whole lot, and including we have this whole long string. Now this file would not work for you if you didn't have your MATLAB set up exactly the same way mine is set up. So what do I do about that? Well, I might think about perhaps importing a function, creating a function instead. So if I generate a function, what it allows me to do is it allows me to pass in a file name instead. And now you'll see it gives us an example, the one we just used, but instead of using the actual hard-coded file name, it comes here and it reads the file name in. So I can save this. Let's save this as import data. And now I can say, well, let me clear all my data out. I happen to have a nice shortcut here for doing that. I can say X equals import data, and I have to give it the name. And I can say it is source signal.csv. And when I do, if we look in our workspace, we get the same data back again. Okay. Well, that's nice, but remember, if I want to loop over it or think about it, I want to make sure this is really more general, and it is. So for example, I could look to that folder that had the data in it, and let's look for what's the name of one of them. One of the name was Jenny. Jenny. Oops, I have to type it correctly. And you'll notice, uh-oh, this didn't work. Okay. And it says, check the path or file permissions. Well, it turns out it's not at the root. I forgot to put in a dot there. So I'm going to use command line recall. The the error messages in Matlab are generally pretty helpful. And I'm going to say from the current directory, navigate to data and then find it. And when I do, you'll see here that now I have a different data set. I'm going to just reset it to the other data set because I want to use the data that we started with here. So I now have that. Now, if I come over to my variables here, whoops, I need to look at them in the workspace. If I come over here, I can look at it in the workspace and I can select the data. Now, one of the things that how do I know if I loaded the data correctly? Well, I don't. I mean, I could open both files and try to compare them one to one. That's pretty tedious. But what I can do is I can make a plot. That's a nice way to summarize things. And what you'll see when I come to the plots tab is when I have data selected, it will show me the different kinds of plots that are relevant for that kind of data set. In this case, I'm just going to use plot. And what you'll see here, wherever it went, let me find my Matlab plot. Here it is that we have some signal with a bunch of tones going on it. Looks like tones, and then there's gaps between them. But I got to tell you, if I took a plot like this to my manager, he'd not be thrilled. And it's not because the data is noisy, but there's nothing here to say what the data is. So I might want to do something about that. And I want to think about that. But before I think about that, I already am thinking about automation. I want to be able to import something, and then I want to be able to plot it. And so if I come over here to the command line, I can get the history, and I can say we want to import the data, and we want to make a plot. Because when I made that plot, it actually added it to the history. And I'm going to right click, and you'll see I can create a script, a live script, or a favorite. Well, I'm going to create a live script. Okay, and we don't really need plot twice. Okay, so let me tell you a little bit more about live script. Let me change this. This will be our main script for right now, main.mlx. You will notice if you are a MATLAB user and you're not used to live scripts, that this has a different suffix. It's a .mlx file, not a .m file. And there's the live editor tab of the tool script that comes up rather than the editor part. Well, what can I do with this? Well, one thing is I seem to have code here, and I could run a section. So let me get in the code, and I'm just going to sit there and run it. And now you'll notice something that's kind of interesting, and that is that in my live script, it actually is collecting the input and the output artifacts as we go, which is really kind of nice. And then I can view it inline like this, or if I don't want to show anyone the code that I'm using, I can hide the code. But I'm going to show the code because I think that's really helpful right now. So I said this is a live document, and you saw me because I was able to run it live and make a change. And you'll also notice that I can do things here, like if I wish to, I can zoom in. And notice MATLAB offers to update my code. If I always want to zoom in like that, I can do that. And I get to do the have the advantage of doing interactive exploration and also garnering the code from that without having to guess what those numbers were. I'm going to undo that for the moment because we don't need that. Zoom out here again. We don't need that. Okay. Now, the other thing that I can do is I might want to come up here and I might want to, for example, insert some text so that people can see what's going on. And I don't need it to be that text though. And what I'm going to do is I'm going to put in a title, and I'm going to say, this is working with audio files. And maybe I will put in something normal, whatever I want to say, showing my boss how to do this. And then I'm going to come here and I'm going to put a heading and say, first, whoops, first let's import the data and visualize. And you can see I'm beginning to make a real document out of it. And I can even come here and I can insert a bunch of different things. One is a table of contents. So it will basically pick up my headings and make a table of contents out of it if I want to. And you'll notice I can put equations and hyperlinks and images and all kinds of things in. So it's a way to gather all the artifacts for what we're doing and show people exactly what we're doing. And so it's very transparent. It's easy to share. It's portable. You can run this as long as you give all the supporting code that your colleague might need, he or she could run it on their machine just as well. Okay. So I can read in the data and I can plot it. And remember, one of the reasons why I wanted to make the importing a function instead of a script is because I wanted to be sure that we didn't hardwire in, for example, that file name, so that we had some flexibility with this, which we wouldn't have had with the script. Okay, now I'm going to come back to my plot here, because this is, whoops, I didn't mean to do that. Go away. Well, let me run this. It wants me to run it, and now it shouldn't be a problem. Okay, so now one thing I can do is I can come over to the figure here, and we can start doing things that would make it easier for our manager to understand what it is. So what's X label? X label is going to be something like samples. We haven't told it a sampling rate or anything yet. And I'm going to put a Y label in, and I believe the measurements for the audio are in volts, probably microvolts. I don't really know for sure, but at the moment that's good enough. And this will be time sequence for audio signal. Okay, so that's already a little bit better than it was. And the nice thing now is if I save this file and I rerun it, even if I change the name here, what's going to happen is we will already have the information encoded in here for putting the proper labels on. So once I do that, Matlab basically behind the scenes generates the code for that and keeps it available so that you end up with a sensible output by the time you're done. Okay, I am now ready to say, okay, how do we know if this is still right? I mean, this looks okay. It looks like something happens for, I don't know, 0.2 or 0.3 seconds, and there's a little gap and so on. But I might like to hear it. And so one thing I can do is let me put a section break in. Nope, not there. Let me undo that. Let me come here to the end. And now let me add a section break. And I want to play the sound. Whoa, my mouse gets enthusiastic. Sound of X. Now it says FS. Oh, let me come back here for a moment to the current folder, and let's go back to this data file we had. And you'll notice here there is a sample rate in there. So we actually know what we want. I'm going to actually come here and say FS, our sampling rate, is equal to 8,000 hertz. Whoops, 8,000. And then when I do sound, create the sound, I'm going to put in the sampling rate here. So Matlab gives us affordances and helps us figure out what sorts of things go in the commands that we're typing. And let me try this out and listen kind of carefully. Uh-oh. I have to import the data. What doesn't it like? Let me go like this. I use run in advance so much. Oh, I have a typo. Sorry. Now, did you hear, you could hear that it sounded like when you type on a phone pad, but did you also hear it was kind of fuzzy? I'm going to play it one more time. You hear that? So that fuzziness is, there's some noise in there that we need to think about. And in fact, we can see that. And again, I sort of showed this to you before, but when I zoom in here, in between each key press, I have a fairly substantial amount of, from an amplitude point of view, amount of noise compared to the signal. And so what I might want to do is I might want to come to my workspace. We've got X selected, and I might want to see what kind of other plots, given that it knows that it's a one-dimensional vector, basically was the way we're representing the signal. And you'll notice there's all these different kinds of plots. But if we come down to the signal processing area, you'll also notice that there's all these different ways of computing spectra of various sorts. And that's a way for us to figure out something about the frequency content. So before I go do that, let me just come back to my slide for a moment and explain what's going on. So what is spectral analysis? Many of you know what it is. In fact, all of you know what it is, even if you haven't studied it. So if I take a prism and I put white light through it, what happens is the light diffracts, and we get light of different frequencies as we after it passes, the light passes through the prism. So this is basically akin to taking a time domain representation of the data, the audio signal, passing it through a Fourier transform, and then getting the frequency contribution, how much was in the 750 range, how much was in the 600 range, and so on. And we basically are able to break our signal down into components that are at different frequencies. And that's all I'm going to do when I come over here. I'm going to come and select from the Plots tab one of these, and let's just take the Periodogram. And now you'll see, and this is interesting, let me make this just a little bit bigger, that I seem to have 7 frequencies here. So I've got the 4 rows and the 3 columns, which were higher frequency. And then you'll notice past some normalized, past some range, I've got this big hump of other stuff that has nothing to do with this, but it is making it noisy when we listen to the signal. So I might want to think about how to do something with that. And what I want to do is do something called filtering. So that brings me to the next concept. What is filtering? And filtering is the ability to separate some parts of a signal from another. In other words, to let some parts of information continue through and get rid of some pieces of information. And even if you've never done this in signal processing, you've done it before because you've probably used sunglasses, or you notice with the coffee filter, what we do is we pass the water through the coffee grounds. We try to keep the grounds back, but we let the water drip through the grounds so that they have an effect, and we get coffee out. And that's the idea behind filter. So what I want to do now is I want to figure out a little bit more about how I can do something here. Well, before I do, let's see what's happening. We just said we picked Periodogram. Let's pick Periodogram in the documentation and take a look. And in my mind, the documentation is one of our secret weapons. Hopefully not so secret that you don't know about it and don't use it. It's really well done. Many of the documentation people have masters or PhDs in their respective fields. Some have even more than one. And they write really high quality documentation, I think. And let me show you a little bit about what's on this page. What you'll see is the syntax, like we're seeing here, the different ways I could call it, and it will give a description of what it's doing. It's going to compute the power spectral density. It will give examples. Examples are awesome because if there's an example that does something similar to what you want, you might not need to read what every single one of the inputs is, because in this case, you can just give it one input, or maybe you want to give it a bunch of other inputs, and maybe you have to specify them this way. Okay, and then there's information about all the input arguments, all the output arguments, and one of my other favorite areas is the see also. See also is good for so many things. First of all, it tells you when the function got introduced in case you're using something new and a colleague is using an older version. One is because it will tell you about some other functions that may be useful to you. If you thought this one was useful, but maybe it wasn't exactly what you wanted, maybe there'll be another one. And it will tell you if there is one, for example, about apps. Well, what are apps? Well, if you come back to Matlab on the apps tab, and I hope you've looked, what we'll have is a whole bunch of icons there from different toolboxes. And you'll see I have a bunch of apps that I've listed as my favorites. I've got apps that I've created or taken from someone else. In fact, what you'll see here is that I have an app that's relevant for this particular application. I have something that will generate phone tone signals for me. And so if I'm doing that, then think about it. I have to know how to generate those, which means some of the analysis work that we're going to be doing is kind of getting put in here to help us figure out how to create the tones. And what I can do is I can delete some numbers, and then we can come here and put in a number. And if I want to, I can listen to the number and I can save it. So we can save it here. So an app is a nice way to take something that might otherwise be tedious. And notice in this case, I don't even need to know the algorithm for how to create the signal. It's presumably got this built into it. So you could give this to someone who just has a list of phone numbers and needs to generate tones for you. Okay, but I've got other apps here besides the ones that I have put in. And you'll notice that we've got ones for machine learning and math and statistics. If we come to signal processing, you'll see there's a whole bunch. And one I want to point out to you, because it's one of my favorites and it's useful and we're going to use it now, is the signal analyzer. And I'm going to bring it up, and here it is. And what I want to do is take a look at the data that we have, and here's my signal. Now, before I get started in earnest trying to figure out what the different frequencies are here, I kind of have a problem. I know this is an unlabeled plot. Well, it's sort of unlabeled. It's got samples. It doesn't know the units here, but these are just samples, so it doesn't tell us anything about time. And I might want to convert that into basically the correct time. So if I give it the sample rate and start time, that might be helpful. So I'm going to give it the 8,000 hertz here. And what you'll immediately see is, oh, that signal's around 3 seconds, a little bit longer. So now we have sensible units because 3 seconds seems about the right amount of time for that. Now, what do I want to do? Well, I want to look at a bunch of things. So for example, let me first look at the spectrum. I had showed you the spectrum before, but in some ways, this isn't an honest representation of the data. Remember, because at any given time, I didn't actually activate all 7 frequencies that are part of the standard. I only activated 1 row and 1 column for each one of these presses. And so there's a bunch of ways I can look at that. One way I could look at that is I could look at what's called the persistence spectrum. And when I do, you'll see, oh, that noise is there all the time, but then you see these different frequencies are there, they're prominent, but they come in and they come out. Well, let me come back to the original spectrum there. And then I can also, we can also take a look sort of a little more carefully here. So I can put the panner on, and let me come down here, and let's get one key press essentially. And now I can come here, and now you see I have 2 frequencies, and I can move along, and I have 2 more frequencies. And so I can pick out 2 frequencies at a time, and that's kind of cool. So we already are beginning to see how we might end up with an algorithm, and that's kind of useful. So let me just make this whole again, and I'll turn the panner off. Another way to look at that information is to look at it in terms of what's called a time frequency or short time frequency, short time Fourier transform plot. And what you see here, let me orient you. This is still time now here, not frequency anymore. Frequency is here. So at any given time, I can look vertically and get a slice of what's happening in the frequency space. And you can see I can get 2 peaks in each of these columns, if you will, but then I still have a whole bunch of noise. So the first thing I want to do is go back and think about that noise. And in order to do something with that noise, I had the ability, if I want, to come over here. You'll notice that there's a way to pre-process this signal here. And so if you think about it, these are the different kinds of pre-processing choices I'm given, or I could add a custom one. If I want to keep the low frequencies and get rid of the high frequencies, I am letting, in the nomenclature of signal processing, I'm letting the low frequencies pass. So I want a low pass filter. Okay, so I want a low pass filter. And if I think about where it was, I should have come back here. Let me come back here for just a moment. Let's put this on. If I look at this, it looks like if I start cutting things off at around 1600 hertz, I should wipe this out, but I shouldn't hurt my signal too much. So I'm going to come here and I'm going to put a frequency for the pass band to be 1600. And it's going to overwrite my signal. I don't want that to happen. So I'm going to come over here and I'm going to say duplicate. And now what I'll do is I'm going to low pass filter. It's okay in this case if it overwrites it. And now what I get to do is, first of all, see the filter response or the data through the filter data. You can see our 7 peaks, but you can see in terms of power spectrum dB, which is a logarithmic scale, I am down quite a bit. And so we've really suppressed the noise that was at those higher frequencies. And we can see that down here too, because the highest values, which are yellow, are no longer showing up in this upper band, but really only down in the bottom. Okay, so let me come back over here and maybe we don't need the spectrum anymore. And I could come now again and we could use the panner. And let me set up the panner here. And now you can see we can come along here and maybe we could read off the frequencies. So that's the kind of analysis I might want to do. And if I wanted to, of course, I could change some aspects of the spectrogram. If you think about it, I don't really want the first section to overlap the second section because they're distinct key presses. So right now the overlap in my my analysis is 50%, but I can change it to 0. So I can come back here and we can see it doesn't actually change things very much, but I get a slightly changed response down here. When I get all done, boy, it would be awfully nice to save this so that if we wanted to apply this to other functions or find out how it was doing this behind the scenes, we could do that. So I generate my function and it's not doing a whole lot there. That's not what I expected. Let me cancel that. Let me get to my signal analyzer again. That's not it. Let me come over here. I'll find it this way. Not that one, this one. Okay. And oh, that's why it did it, because it did it on my smaller thing. I can come over here. I can put the spectrum in as well. And I can turn the panner off now. And now I can say what I'd like to do is generate the function. And okay, so we get, it's just doing the pre-processing. I'm doing something silly and I don't know what. I'm just on the pre-processing side. Okay. Well, that it doesn't matter. The point is that when I do something in here, it can get recorded as a sequence of actions that I take in here can get recorded so that you can then reproduce what's going on again. And in fact, I will come back and do that one more time, because the one thing that you can see is that no, it's not doing what I want. Okay, it should be telling me that we're computing a periodogram, and so that we could see the code for that. And I'm just, oh, that's just for the pre-processing. Aha, close low pass. Now if I generate a function after I've done the pre-processing, no. Okay, I'll get it right at some point. Display, time, frequency, spectrogram. Okay, I'm not going to fuss with it, but the idea is that you should be able to get the code out that you needed to, so that you can reproduce what's going on. Okay. And what I'd like to do now, in the interest of time, is to close this analysis out. I'm not going to save it right now, and I didn't want to save it. And what I'm going to do is I'm going to come over to not the main file that we created earlier, but the one I showed you much earlier, which is my original document that I wanted to show you. And what I'm going to do is I'm going to clear everything out of my workspace, and I'm going to clear all the output out of here. And now I'd like to run this. And what I'm going to do is minimize the tool strip so we have a little more space. And I'm going to make this just a wee bit taller. But what you'll see is from my live editor tab, I have taken run in advance. And if I click on it, you'll see I already added it to my quick access toolbar here, so that I can run a section, run a section, run a section. I'm going to spare you listening to the sound again. Run a section. And now you'll notice that this is the same plot that we had over in the tool, but instead of giving it just the frequency and it converting everything for me, I actually am doing the conversion in Matlab to get the time values for those sample values. And it's pretty simple, but it's something that you need to do. And now I can plot the signal versus time, and we see that it's around 3.2 seconds. And I already showed you the sample signal analyzer, so I'm going to skip that. And we can create the spectrum like we had before. I'm using a slightly different technique, but this is basically, you see the same 7 frequencies, the 4 low ones for the rows, the 3 high ones for the columns, and then the noise that we had before. And if you want to, you can come, and there's another way, rather than the way in the signal analyzer, to design filters that have a bit more flexibility. So if I come down back to the apps and look at signal processing, you'll see that one of them is a filter designer app. And what it allows me to do is have control over many more of the specifications. So I can do low pass in different kinds and high pass. And if I know what order I want, or I can ask it for minimum order. So you can see I have a lot more choices. I can make it FIR or IIR, and we can put in all the information and get a very specific kind of filter out. And from that, we can generate code. Well, I did that already a while ago, and that's what my touch tone low pass filter is here. So I'm passing in information. I'm going to get the filter out, and then I want to apply the filter. And if I want to see what the filter looks like from a filter point of view, I can use this tool, FB tool, and you'll notice that if you want, you can look at things like phase delay and group delay and things like that. You can look at it in the step response. You can look at it at the pole zero plane. Whatever you'd like to do, you can check it out there. Okay. And I'm not going to play the sound again, because but I think I did this, but just in case I didn't, let's get the clean data set up. Now, we've got to the point where we have our cleaned signal, but we haven't in code picked off the different frequencies. And so that's the thing that I want to look at. And so what I'm going to do is I'm going to come over here, and I'm going to show you how we did it. You'll see that I have some functions I'm calling here, envelope and fall time. Well, if we do help, I just right-clicked and I'm bringing up that wonderful help again. And here's a signal envelope, and I tell it how I want it to find the envelope. And I'm also using fall time. And so when I do this, what happens is I'm getting an envelope for the signal, because remember, I have a whole bunch of up and down oscillating. And really, I want to look at the sort of the envelope for it. And when it falls to very small values, that will be the end of the key press before I get to the next key press. So I'm saying essentially that when I get in here after I filtered it, that when I get in someplace like here, when I filtered it, that should be the end of that one, which would be the beginning of the next pulse, and that would be the end of the next pulse. So the way we accomplish that down here is with the envelope function, and then looking at the when it falls to a certain level. So here we get the RMS envelope, and so what I'm going to do is I'm going to plot where that fall time hits each time, and then I can count how many times I've hit that fall time. That's how many pulses I have. Now, the reason that's important is surely you have been in a situation when you're traveling around, especially, not all phone numbers are the same length. When I call phone number within the US, I have to dial different numbers than I need to when I want to call home when I'm in Europe or Asia or Australia or wherever. I usually have a sequence of anywhere between 2 and 5 precursors that I need to type before I type in the actual phone number. And so we don't want this to be dependent on, oh, I know phone numbers are always 11 digits or 7 digits or whatever it is. So what we do is we find what the mean pulse duration is here, and you can see it's about 0.3 seconds. And so I'd like to find which 2 peaks are relevant for pulse number 1 and pulse number 2 and so on. And so what I'm going to do here is I'm going to compute that spectrogram, again, with no overlap this time, with the clean data. And here we get it. And here you can see I've got my two frequencies, and I can read them off, but that's not very automated. And so what I can do instead is I can use the spectrogram function to return the information for each one of these areas, each of the 11 pulses. And then what I'm going to do is I'm going to loop through the pulses, and I'm going to use this absolutely fabulous function, find peaks. And find peaks has a whole bunch of options here for how I might identify peaks. So I can tell it how many peaks I want. In this case, I want 2. I can tell it whether there's a minimum height that I want or how prominent. So the difference between height and prominence is sort of height is absolute, and prominence is going to be how far does this peak come up above the other stuff. So it's relative in some meaningful way. So and then I can set the thresholds and different things like that. And I can say, don't count 2 peaks if they're too close together or whatever. So I can come here and I can find my peaks, and I can get, what you see is I get frequencies in 2 sets of frequencies. I get basically the lower frequency and the higher frequency. This would be the row frequency and the column frequency. And so I need to think about identifying which keys those frequencies correspond to. Now notice these frequencies are, they may not be exactly integers. Some of them are, but I have like 1210.5. And yet the frequencies we have down here, which are part of the standard, are all whole numbers. So that's okay. I still want to find the frequencies that are nearest, but I only want it to be counted as near if it's really close enough. If it's really, you know, if it's 1800 hertz, I don't want to count it as 1477 here. And so I'm going to just set up the row frequencies are this list and the column frequencies are that list. And here's what a standard keypad looks like. And so there's the keypad. And now what I want to do is I want to use this great function is member tall. I'm going to give it a tolerance, and I'm going to take the row frequencies, compare them to the row frequency list, and with a tolerance, and I'm going to give it a small tolerance. I don't need a big tolerance here, fortunately. And when I get my rows and my columns set, what you'll notice here is that I end up with the decoded phone number, which happens to be MathWorks headquarters. So I didn't give anyway someone's personal numbers there. All right, I want to come back to the slides for just a moment. So what we did, remember, is we figured out a way using the import tool to load the data in. We then noodled around for a while to figure out how to do the analysis. We took all of that and we automated it. And now, if I wish, I can come here. Whoops, I can come here and do some reporting. So this is our full report. And if I wish to, I can come to the live editor. I'm going to make this come down again. And I can save it in a bunch of different ways. So I can save it to a Word document, for example. And we'll go like this. And once again, I can then hand this off to someone. They don't need Matlab. They get all the benefit of what I've just done. You'll notice that if I want to, I can remove all the code from them seeing it, and I can just show them the results. If you want to do that, you can then make a document, and that document would be similar, but it wouldn't have the actual code showing in it in the same way. Okay, so that's one way of letting people get access to the information. But remember, I also had that app. So there's other ways I could make, maybe the phone tone creator, that might not be the app. Maybe I want a decoder, but if we just take that phone tone creator, that might be the kind of thing that we want to use. And so what I want to do is think about how we can share the results here. So we could take this and package it up as a toolbox. We could deploy the application to other environments, and we can actually create I don't want to spend time on that. What I want to do is come over here. So let me come back to here, and I'm going to come to my project, and I'm going to show you how to do app designer and deployment. And if I come to my current folder, okay, so now what I can do is I can open up the app that I've created before. You saw the app running. But now I'm opening up in the app designer environment. So this is where you might want to develop an app. This will look very familiar to you. And so it's very easy. I can come here, and you'll notice that one happens to be app button 1, and that's app button 9. I did that on purpose so that the buttons and the numbers matched up. But this is just the design look, and I could add anything else I wanted in here. If I wanted to put something else on, I could add it. For example, I could put, I don't know, we could put a little image on that we put an image in and add that if we want. But I can also look at code view, and we can come here and I can say, what happens when I look at button number 1? And so if I look at button number 1, we can begin to see for the code what's going on. So there's a way of saying in here what I want to do. And so you program in what's called these different callbacks. When I push the button, what will it do? And then when you're all set, you can come back and say, okay, now let me try it and run it. And now I'm going to have this thing with a funny image on it, but it should run the same way as it did last time because I didn't change any of the other code. And now I can add a few digits on. And if we want, we could save that to a file. And so that is very quickly one way that you might want to, and the way we recommend to think about creating apps. And then you can take those apps, and depending on how you package them up, you can choose to share them with other people, either with Matlab or without Matlab, as long as you have the right extra tools from us. Okay, and that would be royalty-free sharing as long as you have the Matlab compiler to share it with. And I'm going to skip some of this now. I also want to mention very briefly that there is a very large community of MATLAB and Simulink users. You can go over to mathworks.com. There's MATLAB Central, and we have a whole bunch of different things. We have blogs, MATLAB Answers, Cody, which is a coding contest, File Exchange, Internet of Things, which is ThinkSpeak, and a forum for asking questions, answers. It's called MATLAB Answers. We also have training. So if some of this is interesting to you and you didn't catch everything, that's fine. For many of you, if you happen to have campus-wide licenses, you may well have already much of the training available to you on your campus. Check your campus license if you have to. If you can't figure out how to do that, contact us at MathWorks and we can help figure out what you have access to. And I would like to see if there's any questions that people need to have answered. Let's take a second for people to shoot me some questions if need be. You're all experts. All right. Well, let me just remind you, the goal today was to come in and show you MATLAB and how you may use it when you have data that's represented in time and frequency. So basically signals are your data. And I was able to show you things like the live script that you could share. I was able to show you apps we could use. And in all the cases, we were able to automate. We were able to generate code so that we could automate things rather than doing them by hand and by mouse all the time. I gather there's a question on zero crossings, but I'm waiting to find out what it is exactly. Okay. What is the best way to detect zero crossings in a signal? Well, I don't know. I'm not sure, but there are a bunch of ways. One way that it depends what you have access to. What I often do is I just do, let me just see if there's anything here. First of all, zero cross. Whoops, I have to type it correctly. That's Simulink. So if you happen to be using the DSP system toolbox, there's a block that will tell you that. But basically what I would do is I would take a diff of the signal. So that would take a difference between each successive pair of points. And I would look to see where it changed sign, because if we're crossing through zero, you should see, well, you could look at, well, it depends on what you're doing. Yes. You could look to see where the sign is different, or you can see where, if you're just looking at your signal, you can see if it's something that actually does go up above and below zero. You can find the next place where it's less than zero, and then wait again until you find another place. You can use the find function essentially to find the locations where it goes below zero, and then find the next one after that that goes above zero, and the zero crossing would be in between. So hopefully that made some sense. Finding zeros. See if there's anything there. Find steady point, find an operating point. Those are all, let's look for MATLAB. Those are for functions. You might want to use the isChange function. That's an interesting one as well. An isChange function lets you take a signal and find out when there's something interesting going on, and your choices are listed in here about what you might be able to do to find it. Okay, so if that's all, I want to thank you very much for spending the time with us today. We've put some links in the description below that you might find interesting. I want to point out two events in particular. The first is the Matlab Expo 2020 on demand, and it's an online site featuring technical talks covering a broad range of topics where MathWorks products are used and play a central role in the work of some MATLAB users. The second is we have an ongoing active Simulink contest. So if you're thinking of learning Simulink, now may be a great time for you to try, because it's a challenge in which you could possibly win $1,000. And with that, I want to thank you. And I want to remind you to please subscribe to the MathWorks channel to get reminders for all the upcoming events. I look forward to seeing you next week. Thanks.